Hello and welcome back to lesson 8. And today's topic is the five key equations for motion. And the goal is I want you to be able to identify the corresponding kinematics equation to apply to a given situation. So very important today. We're going to look at the five equations, and we are going to I'm going to show where they come from, just so you know that they're not created with thin air. And then you're going to have to be able to identify when to use each. And you'll find that it's just a process in decoding at this particular level. But these equations are very key and so important, especially for the students that are taking the grade 12 physics course. All right, so none of these derivations, you don't have to regurgitate anything. I just want you to follow through and realize where they do come from, and they're not some magical thing that we just produce. So, average acceleration. What is average acceleration? Well, it's defined as the change in velocity within a given time interval. All right, we're going to talk about that a little bit later on. Acceleration due to gravity, you talked about that in your grade 9 course. Just want to go back and a quick review, because we talked about this in much more detail in Unit 2. But on Earth, people are able to stay on Earth thanks to gravity. And the average acceleration, or the value that we use here on Earth, average, I don't even spell properly, average acceleration is 9.81 meters per second squared. So in an ideal world, so that means everything is perfect, or a physics world, so they're interchangeable, all objects accelerate toward the Earth at 9.81 meters per second squared. Now, in an ideal world, we assume that we're kind of living in a vacuum where there's nothing affecting gravity. So at this point in time, we're going to talk about more detail about what does affect gravity, or what factors influence how we fall, but that's in Unit 2. So at this point in time, I just want you to know that gravity on Earth, we are using 9.81, and we use, instead of using acceleration, I use g to represent that value. Okay? So just something we need today, and we'll talk about it in far more detail in the next unit. Okay, going back to a VT graph. All right, so this is a VT graph that we've been talking about the last couple days. What I want to do is I want to come up with a couple of formulas for this, or from this particular graph. The first one I want to come up with or look at is just this segment here. So I want to look at this constant velocity. All right, we know that in order to find displacement, delta D, it's the area under the curve. So you don't want to color this in with yours, because it's going to change as I go. We would simply find the area under that graph. And most times, what I want to do, well, how else do I want to look at this? Did I change my slope? No. So delta D, we know that from before, it's not going to come from this graph, that we simply do it by V times delta T. Okay? And that was for uniform motion. Okay? So therefore, if acceleration is equal to 0 meters per second squared, then the formula we're going to use is delta equals V delta T. So there's only one formula that exists for uniform motion, or applies to uniform motion. This formula doesn't apply if we have acceleration, and that's what we have in this graph over over to my left. So that's why I've done that separate. So that is one of our equations that I was referring to. So I'm going to put a 1 beside it. So delta D equals V delta T is one of our equations. Another equation, if we're going to find the area under a curve or area under the line here, we're going to come up with, let's call this T2 and T1. We'll go right back to the beginning. We're going to call that value there V1, and we will call this point here, that height there, V2. Okay, so if I want to find the area, okay, under the graph, so this region right here, the formula would be area equals length times width plus 1/2 base times height. We know that the area under the curve is your displacement, so delta D. For the rectangle, length times width, so it would be T2 minus T1. So that's the bottom here, multiplied by the height, which would be V1, plus 1/2, again the base for this triangle would be the T2 minus T1, and the height will be V2 minus V1. All right, so your delta Y, V2 minus V1 would be that height there. Doing some simplification here. There's a couple things that I do that we can simplify. First of all, T2 minus T1 is the same as saying our change in time. Okay, so T2 minus T1 is equal to our delta T. So that will clean up some of the equation there for us. Next, so the next thing we want to do is make that substitution. So delta D would equal delta T V1 plus 1/2 delta T, and then we have V2 minus V1. So at this point in time, we're going to leave some space. All right, I'm going to work in another area because that V2 minus V1, what I want to do is I want to reduce the number of variables that are involved there, because the equation still, we like to simplify it down. So we're going to go one more line there, and I'm going to show you where that will come from. All right, so off to the side here, or wherever you have space, we're going to come back to that equation. I'm going to finish it off and we'll label it. Before we get there, we have to come up with something, because I want to replace the V2 minus V1. Very clunky at this point. So if I'm going back to my graph again, what I'm going to do is, how do you determine acceleration? Okay, so from our graphs, we know that acceleration, A, comes from slope of Vt. So that's where I'm heading next. So I'm going to find what is the acceleration on this stretch right here. Well, we know that acceleration is delta y over delta x. And what is my delta y in this case? So my delta y will be my v2 minus v1. So that'll be the height of that triangle. So v2 minus v1. And the time, again, is going to be t2 minus t1. So I know that acceleration is equal to v2 minus v1. And that t2 minus t1 is just delta t. If I want to get rid of the fraction, I'm going to multiply both sides by delta t. It's nice if we can avoid those fractions. Inverse operation would give me that. So now I have v2 minus v1 equals a delta t, or acceleration multiplied by time. Or finally, v2 is equal to v1, so I just add v1 to both sides. Just doing some algebraic manipulation. Okay, plus a delta t. So at this point, I'm going to box this one up, and there is our second kinematics equation, and a very important one. Also, going back a step, I'm going to take this equation and I'm going to use substitution into that one. All right, so I'm going to replace v2 minus v1 with a delta t. So delta d equals delta t v1 plus 1/2 delta t. And v2 minus v1 is going to be replaced with A delta T. So in a final step then, to clean this up, V1 usually comes first in the formulas, plus 1/2 A delta T times delta T is delta T squared. So now I'll pause again and box this up. Here is your third equation. Okay, there is your third equation for kinematics. So those are the first three equations. And as I said before, there are there's five that I want to develop here. So heading toward coming up with all five equations then, I've started fresh here on the next page. So I have my T1 and T2, just because I was running out of space. And we have our V2 and V1. So same setup as what I had before. If I want to find the displacement for this particular time of travel, I would have to find the area under the line. So same as what we did the other day. So in this case, our delta D will equal length times width plus, find the area under there, so it becomes length times width for the rectangle and 1/2 base times height. So it does look very similar to how we started the previous question. I'm going to do a little bit different algebra this time. So again, the T2 minus T1, I'll put it in there for this part, multiplied by V1. Plus 1/2 the base, again, T2 minus T1. The height is V2 minus V1. All right, so this becomes delta T V1 plus 1/2 delta T V2 minus V1. So if you recall in the last equation, we replaced the V2 minus V1. I'm not going to do it this time. So in this case, delta T is common. I know there's people that are starting to cringe again. I'm going to pull out a common factor of delta T, which would leave me with V1 plus, and now I'm going to distribute that 1/2 in. All right, so bear with me on this. 1/2 V2 minus 1/2 V1. If I collect like terms, V1 take away half of V1, I would end up with half of V1 plus 1/2 of V2. Now I can pull a 1/2 out, so 1/2 delta T multiplied by V1 plus V2. So there is your fourth formula. All right. So we have four formulas at this point. That's the fourth one. You want to make sure that they're on a sort of a cheat sheet for you as you run your way through, because the formulas are so important. You're going to be using them all throughout the homework. I'm going to finish up the fifth formula in the next slide, and then we'll do some examples to see what exactly we're running into here in this particular unit.